In my last video, we discussed Ruth-Hurwitz's criterion as a necessary means for developing an algorithm of stability for a given closed-loop transfer function. In this video, we're going to expand on that idea, first by proving that for a set point unit step change, we can always use an additional control parameter to minimize/eradicate offset in the system. Subsequently, we're just going to test kind of this Ruth-Hurwitz analysis again, doing another problem to prove kind of its usefulness here. So, and of course, we're going to simulate all this at the very end as well. So let's jump right in here. Our first prompt is using the final value theorem. We want to show that with PI control, a second order process will always reach a desired set point. So we got a lot of information in this, and it seems really complex. But first, I think it's going to be most important to define the final value theorem. And what the final value theorem says is that the limit as t approaches infinity for some function of time is going to be equal to the limit as s approaches 0 of s times the Laplace transform in the s domain of that function. And so using this theorem, we can go ahead and determine what the long-term behavior of our control loop will be. So let's go ahead and start with drawing kind of another process block diagram, just to familiarize ourselves with what system we're really talking about here. So we're going to start with our set point, Rs, and we're going to have that meet with maybe. Basically, this will end up meeting with, oh, wrong way. The output of our loop. So Rs is going to go into our closed loop and subtract our output from the last run of the cycle to get our error function in the S domain. Obviously, in control block diagrams, as previously discussed, we're going to stay completely in the S domain. Then the error system is going to go into our first block here, which will be a representation of our controller transfer function. And then we're going to define a term US here. That's going to be our input, which seems kind of counterintuitive because it's coming out of our controller. However, this input is what's going to be put into the process block here. And so this denotes the physical change that our input will have on the process as a transfer function. And then we are done, basically. So coming out of that, we'll have our output y of s here. Sometimes, and this isn't going to be particularly pertinent to this video, as we're told to assume that this block will be 1. However, generally, our measurement device, or GM, will also have a gain associated with it. And so that block there represents kind of our measurement. And so that is kind of a generic control block diagram for any process. Using prompt 1, let's kind of denote what exactly our process has specifically that we know about it to go ahead and apply this final value theorem here. So we're told that we have PI control on the system and that we have a second order process here. Again, what we're attempting to do is measure offset in this case. So I think it's pertinent to kind of define offset with some sort of meaningful relationship here. And so what offset is really going to look like here, offset, and again, what is offset really? Offset is, for our process, you know, here is our desired set point, and here's our process curve. So at long-term time, right? And so offset is defined as this distance here between our equilibrium process condition and our set point. So how can we define that kind of mathematically in these terms? Well, offset is going to be the limit of what? We want it to be the limit as t approaches infinity, because again, we want to be at equilibrium conditions, so infinite time is kind of addressed there. Of what? Our error function. And since we're in t, we have to make that a function of time. Well, according to the final value theorem, that will simply be the limit as s approaches 0 of s e of s. And this capital is usually used for the Laplace domain. I'm not going to use it here because I didn't use it in our control block diagram here. So we simply need to find our e of s function, and what we need to do with that then is multiply it by s and take the limit as s approaches 0 to find what our offset will be. And again, we are attempting to show that there will be no offset because we will be always reaching the desired set point, right? Okay, so let's do this. Basically, what we know about the system, what do we know about error? Error is, we know that e of t is going to be equal to what here? It's going to be equal to r of t minus y of t, right? And so thus we can make kind of the same analogies here. Remember, Laplace transform is a linear operator. So we could say that e, again, I'm dropping capital notation just because I didn't use it in the control block diagram. E of s is going to be equal to r of s minus y of s. Yes. And again, we want s to be approaching 0 here. We can rewrite this equation then, right, as r times, well, r of s rather, times 1 minus a of the closed loop. And the reason we can do that is that r times our parameter, we call that a parameter, our k parameter, our proportional parameter for our closed loop will be giving us our output condition there. So at this point, r of s is our set point, right? So we just need to figure out what is k of the closed loop. And if we can get k of the closed loop to always be 1, then there would obviously be no offset here. It would be equal to 0, right? Yes. Yes. Let's try this. I'm not sure that I've written this completely correctly, so let's attempt to try it. and see what happens here. So let's go ahead and define PI control parameters here. So PI control, for just proportional control, right, we said that the gain was going to be equal to Kc. Now for PI control, we're going to say that the gain will be equal to Kc plus 1 over 1 Kc times the quantity 1 plus 1 over tau I times no, wait, I'm writing it the wrong way. It needs to be Kc times tau I s plus 1 over tau I s, right? So we know that's our gain function here. Our two tuning parameters, and we can get into why we call them tuning parameters. This is going to be a little bit more featured in the next video. But our tuning parameters are Kc and tau I here. Now, we also know that it's a second order process, which means that our process gain is going to be what? Well, it's going to be Kp over tau p s plus 1 squared. And that is a second order process transfer function here. Awesome. Now, for the closed loop gain, we know that that's going to be equal to what? And here comes all of the algebra that we've been waiting for. It's going to be GC GP 1 plus GC GP. So, we've already defined GC and GP. So let's go ahead and start to plug these in here. It's going to be equal to Kc times tau is plus 1 over tau is times Kp 1 over tau p s plus 1 squared 1 plus Kc tau is plus 1 over tau is Kp 1 over tau p s plus 1 squared. Now, I'm remembering why we could use this and attempt to simplify our, sorry, my line just came through. We could use that relationship and attempt to minimize our offset in that way, or what we could simply say is, what is the, man, I'm blanking on words right now. We could say, what is S times the closed loop gain, and if that closed loop gain is zeroed, then we could also figure it out that way. So let's walk through this, and then once we get to the answer, I think it will be fairly evident the words I just said in a correct order here. So gain closed loop is going to be this. And so the first thing to do with this, to simplify it, because this is messy, again, remember Kc and Kp are not the same value, and that tau I and tau p are not the same value. Those are very different parameters here. One depends on the process, one is a tuning parameter of the controller. So Here we go. I'm gonna have to sneeze. Sorry. Okay. First thing to do here, let's try and pull in some of these fractions into the same thing. So I'm going to go ahead and define this value here, our numerator, kc, kp, tau I s plus 1 over tau I s tau ps plus 1 squared. And again, not the same thing. We can't cancel off this squared and this. That does not work because our taus are different values. So the reason I wrote that out is because this one function comes in a bunch here. So it's going to be our numerator, and then it's also going to be a piece of our denominator, 1 plus that. So that's getting somewhere, right? Now, for this guy here, what we're going to do algebraically is combine the fraction. So let's rewrite 1 as tau I s and tau es plus 1 squared over tau I s tau ps plus 1 squared. And now we're just going to add these fractions across here. So again, this will remain on the top. And what are we going to have? We're going to have AC, AP, tau I s plus 1 plus tau I s tau p s plus 1 squared over tau I s tau p s plus 1 squared. Okay, now we have a complex fraction, so let's flip and multiply here. So numerator times denominator, but it has to be the inverse of the denominator. That's how algebra works. Carrying out this multiplication, it's pretty easy to see. This is going to cancel, and this is going to cancel. And so we're left with this guy over this guy. Okay, so now we're getting somewhere. The next thing that we're going to go ahead and do here is we're going to, again, what form are we really trying to get to? We're trying to get standard form, which looks like ACL over tau CL S plus 1, right? So what we want to do is we want to have no S's on the top. Basically, we want all of our S terms consolidated with this tau S term right here, right? And so how are we going to do that? Well, we want to pull out. Let's try this. So I'm going to divide. What am I going to do? I think I'm going to multiply the top and bottom by 1 over tau is plus 1. Does that work? Let's see what that does. Actually, what if we make this R1 instead? So let's divide. We're basically going to divide by tau is tau ps plus 1 squared on both the top and the bottom. Okay, so what will that give us? That will give us kc kp tau is plus 1 over tau is tau ps plus 1 squared over kc kp tau is plus 1 over tau is tau ps plus 1 squared, right? Plus 1. So now we can already see we're getting kind of close. And so what can we do here? We could do divide the bottom again by that term. Yeah, let's try that. So now what I'm going to do is divide off of our s terms here. So let's try it. Kc Kp divided by, basically I'm going to multiply the top and the bottom by tau is tau ps plus 1 squared over tau is plus 1. And so that'll give us kc kp over 1 over kc kp plus tau is plus 1 squared over tau is plus 1. This should be a tau ps, right? Okay, so now we're very, very, very close. So let's divide both sides now by kc kp. Both sides, I mean the top and the denominator. So that'll be 1 over tau is tau ps plus 1 squared over tau is plus 1 times kc kp plus 1. Now we've done it. We've gotten ourselves a standard form. So again, we can see GCL of S, our closed loop gain, is simply 1 over tau is tau ps plus 1 squared over tau is plus 1 kc kp plus 1. Which of course implies that our k is 1. Now, by the relation that we derived above, related to the fundamental value, oh my goodness, related to the fundamental value theorem, we said that offset is going to be S times RS 1 minus KCL times, of course, whatever our change is. Now, we said we're going to do this for any unit step change. So we should have 1 over S, or rather A over S, as our, this is the Laplace transform of A, right? Where A is a step change. So obviously now we can see that S times S will cancel, and we're left with R of S times 1 minus KCL, which is 1. Obviously this goes to 0, and so our offset is 0, which is what we predicted initially, correct? We said always reach desired set point. Well, the set point minus the output is our error, aka our offset, and we just determined our long-term offset will be 0. Thus, with PI control, our second order process will always reach the desired transfer function. Now, the other thing to kind of take away from this derivation in its entirety is that it really isn't order dependent in terms of the process transfer function for our process gain, right? So we gave it a second order process just because that's what the problem stated. However, excuse me, remember that what's really being changed, depending on the order of the process, is the order of the tau ps plus 1 term. However, this derivation would work for any order because, again, that tau p plus s, tau ps plus 1 term is being canceled here and is only appearing once in its native form in the closed loop gain function here, right? So truly, we could kind of expound or extrapolate this idea to occur for any order of a process gain that can be written in the standard order process transfer function nomenclature, right? So basically any function or process gain that can be written as such, where 2 is really equal to n, this PI control will eradicate offset for specifically a step change of any magnitude. Because again, our magnitude here was arbitrary, it was just A, right? So I guess technically we should have A here as well. I missed that piece. Obviously, if A was 1, then it wouldn't have mattered. But for any step change of any magnitude, we have shown that for any order of process transfer function, specifically in this case, we used a second order, that offset will be 0. All right, quick cut. But now we're going to go ahead and move into part 2 of this video, which deals with a specific process gain function. And we're going to attempt to calculate stability criterion from its characteristic equation using Routh-Hurwitz criterion. So the specific process gain function that we're going to be dealing with here is going to be 2 over 10s plus 1 minus 1 over 2s plus 1. Double check and make sure that that's actually correct. Yep. Okay. So we've got this function here. The first thing that we're going to go ahead and do, again, we're attempting to model the system under proportional control, which means that our control gain would just be some constant Kc. So the first thing I'm going to do here is say what is our process gain function. Let's go ahead and combine these fractions here. So we're going to have 2 over 2s plus 1 minus 10s plus 10s minus 1 over 10s plus 1, 2s plus 1. Okay, now we're going to go ahead and define our closed loop gain function as the following. So remember that should be GC GP over 1 plus GC GP, which in this case will simply be, well, let's go ahead and simplify this real quick. This will be 4s plus 2. We're subtracting 1, so it will be negative 6s plus 1 here. Yep. Over 10s plus 1, 2s plus 1. Okay. So then this is going to be multiplied by Kc and go on the top. So I'm just going to go ahead and copy this over. So I have to write it 4 times. So we're going to do that over, well, first times Kc here, over 1 plus Kc times that process gain, right? Okay. So let's go ahead and attempt to combine fractions here. Excuse me. So Kc times negative 6s plus 1 over 10s plus 1, 2s plus 1 over 10s plus 1, 2s plus 1, s plus 1, 2s plus 1, and that's just rewriting our 1 there. And then same things on top, GC, GP right here. Let's go ahead and combine fractions. And what are we left with? I'm actually going to go ahead and invert the denominator after combining as well. And we'll see why here to go ahead and perform the complex fraction division here. So in this case, our numerator will be 10s plus 1, 2s plus 1, and then our denominator will be Kc negative 6s plus 1 plus 10s plus 1, 2s plus 1. So, of course, our forms there will cancel, and we're left with this guy right here. Okay. So I think the next thing to do is to divide the top and the bottom by Kc negative 6s plus 1. And so when we do that, we're going to be left with 1 over 1 plus ns plus 1. Well, that would be what we were trying to do if we were looking to get it in standard form, right? But we're not looking to go into standard form. We're just looking to have a functioning denominator here. So we really just need to divide by negative 6s plus 1, I believe. Let's see what that does. And see if this gets into a manageable form here. Okay. Okay, so that's basically standard form still. And our goal, of course, is to come up with some sort of polynomial here on the bottom. Hmm. Well, let's see if we can do any work with this. Let's see here. The first thing I'm going to go ahead and do is see if there's any fraction division worth taking place here. And that did not work. Well, well, I think we can still have zeros on top. So let's actually go ahead and keep this guy. So what we're going to need, we need to be looking particularly at the denominator here. So let's look at the denominator, and so let's go ahead and erase the numerator. Reason being, our denominator is our characteristic equation that we're going to be examining the roots of through the Ruth-Hurwitz stability analysis. So let's go ahead and try this. If I go ahead and FOIL this out here, we should get that function. And so let's see. Then I have minus 6s times kc plus kc. So what we should be getting here is 20s squared plus 12 minus 6kc times s plus what? 1 plus kc as our last term there. And so thus, we've gone ahead and constructed all that we need for Ruth-Hurwitz analysis here. And so what we're going to go ahead and do is construct our matrix here. What we should have is 3 rows. Oh, excuse me. Is in the way here. There we go. What we should have is 3 rows. Reason being that the highest order of our characteristic equation here is 2. Ruth Hurwitz's go to n plus 1. So this should be an minus 2, an minus 1, an minus 3. So let's go ahead and do that. So an is, of course, 20. An minus 2 would be 1 plus kc. An minus 1, 12 minus 6 kc. An minus 3 is 0. Now for b, usually this term is quantified as b1. This will be an minus 1 times an minus 2 minus an times an minus 3 all over an minus 1. And we only need to find our left column here, and we need to ensure that all of those numbers will be greater than 0. So in this case, what we need to do then is go ahead and do this manipulation here. So obviously an times an minus 3 is going to be 0, and we're left with 12 minus 6 kc, 1 plus kc over 12 minus 6 kc. So obviously that's going to cancel out, and we're left with simply this term right here as our b1 term. So now the limits of our tuning parameter kc are, of course, limited in stability conditions by the quantifier that they all have to be greater than 0. So obviously for row 1, 20 is always greater than 0, so that is okay. For row 2, 12 minus 6 kc must be greater than 0, which implies that negative 12 must be less than negative 6 kc, or that kc must be less than 2. And then for our final condition here, we have 1 plus kc must be greater than 0, or kc must be greater than negative 1. Thus, we've bounded our kc by 2 of these conditions, knowing that it must be less than 2 and greater than negative 1. Okay, I think that covers prompt 2 here. Let's reread it. Determine the limits of stability for a proportional only controller. Okay, so we've done that. Now we're going to go ahead and simulate this system here to demonstrate limits of stability. So again, what are our limits of stability that we're looking for? We're looking for this right here. We'll test both of those bounds on KC and see what happens in our simulation here. So let's go ahead and jump on over to the lab here. I believe I've already started a file with all of the inputs in it. Perfect. So here's all our imports. I'm going to go ahead and throw my face up here so that we can see what we're doing code-wise here. These imports are to import specifically this S from the SymPy library. Obviously, S is the function that S is the variable of interest that we're going to be writing into our code here, as well as we're importing this sim function from a chemical engineering library. What the sim function is going to allow us to do, as we'll see in just a second, is going to be basically to import our closed loop transfer function, and then throw in a dummy time variable and simulate how that system will respond based on the closed loop transfer function provided. So what do we need to do here? Well, we want to define our closed loop transfer function. Obviously, that's going to be what? It's going to be GC times GP divided by 1 plus GC times P. Some of those are capitalized, not. Right? So, of course, we're going to have to define our two parameters here. GC is going to be KC. C equals KC. No, I just want to be done. KC is going to be what we're going to manipulate here. Let's keep it negative 0.9 for now to test our limits of stability. And then we need to go ahead and define our process function here. So GP then is going to be what? We said it was 1 over, 2 over 10s plus 1 minus 1 over 2s plus 1. Perfect. And times s, I guess. Perfect. And so then let's go ahead and simulate our system here. So the way to do this is that the sim function is going to take an input of our closed loop transfer function. Like I said, kind of a dummy variable for time here. So I think it's lambda t. I think we can just say 1. N is going to be however many steps we want to run. So let's start with 100. dt can be 0.1, that's fine. We'll just see what happens with the simulation and if this runs appropriately. And so what that's going to output then is our t and our y. Obviously, y is our output. Let's go ahead and make sure that runs, so it does. So then the last thing that we need to do here is just plot t versus y. So big equals make subplots. Did I import that? Yes. Big dot add scatter here. We're going to say x is equal to t, y is equal to y, and our mode should be lines. So then finally, let's just go ahead and throw in an update layout. Okay, let's see if this runs. Okay, it does. And then this is what we would expect for our system. Obviously, you can see I named it this inverse response here. So there's sort of an inverse response before the controller really is able to take control. So that was negative 0.9. Let's do negative 0.99 as our KC. You can see it's see. Let's actually run this a little bit farther. Okay, yeah. So we're running pretty unstable there. But we can see if we get back in kind of our bounds of KC, we go to a pretty stable system. Let's go to 1.9. So still oscillating. So oscillations are going to increase here. Here's our inverse response. But we are magnitudes of the oscillations are decreasing. Thus, we should expect that to be good. Again, looking good, looking good. No control. Oops. Guess we can't do no control. With no control, obviously, or virtually no control, you start to see it go flatten out there. And this is a negative, almost no control. So you can still see inverse responses happening, but we're still flattening out. All right, that's the simulation. So that kind of covers part C here. With that, I'll bid you adieu and see you in a second for video number B.